So let us spend some time on understanding the technology behind it as well as the features which you should be aware of as IoT designers. I thought I will start with Wi-Fi so that I can introduce you to wireless communication a little bit before we get into other short range technologies. As you are aware, in a Wi-Fi router, what you have at home, the antenna that is there, normally you will see that there is a single antenna in your wireless router. It may not be visible. Sometimes it may be not a antenna like this. This is called omnidirectional, OMNI, omnidirectional. That means it sends signal in all directions. Okay, the same intensity of signal. So antennas, they come in different ways, and if it is omnidirectional, that means it is sending signal strength in all directions the same way. They are not directional antenna, but some directional antennas send beams like this. Radars fall under this category. They send in a particular direction, the gain is more. This is called directional antenna. Whereas the gain will be coming down in other directions, and then there will be side lobes, they say side lobes, wherein small leakage of signals may be there, but the majority of signal is directed in one direction. That is called a directional antenna. One thing you should understand about antenna is the design of antenna, whatever structure and material and length and dimensions used, decides the pattern, the radiation pattern of the antenna, and based on the direction it will be changing. So you can keep rotating it, then you will be seeing different angle, different directions. Now another thing is, this gain what you see is not only for transmission, it's also for reception. That means, suppose in a radar, what happens is, if a flight is going and then the radar signal is hitting it and then coming back, the reflected signal also will have higher gain so that it will be received by the antenna on receiving side. So the antennas, the gain pattern is uniform and the same for both transmission, the maximum signal is transmitted in this direction, as well as when the reflected signal comes or another device is transmitting, they also receive, majority of the received signal will be received in this direction. Whereas if any signal is coming in this direction, they will not be received because they will be attenuated. Side lobes or less gain in this side is attenuation of the signal. So the antenna can see in a particular direction. It is like a torchlight looking in particular direction. Whereas in a omnidirectional antenna, the signal is coming in all directions. It is like a floodlight in a stadium. Even floodlight in a stadium is focused on the stadium, but you may see some middle of the road, there will be lights on all directions. So they will be spreading light in all directions. So it is similar to light, but similar to light itself because it is a radiation and the frequency of transmission is also same like light. Okay, now what happens? What are the problems with this kind of a communication? Now, when you have a Wi-Fi and then the devices are there, this router is sending signal in all directions. Now, there will be so many devices in that range based on the amplitude of the signal and how far it can go. All the devices are receiving the same signal. They are receiving the same identical signal. They will all receive the signal and they will look into the data or the packet header, and then like a Ethernet, when Ethernet cable you connect it, the same cable or multiple devices are connected. When the signal is sending over the Ethernet cable, all of them receive, all the devices connected to them receive, and then they check whether it is addressed to them or not. If the destination MAC address is not matching with the device MAC address, then it will ignore it. That packet will be ignored. Whereas which is addressed will absorb the packet, will take it inside and pass it on to the protocol stack. So similarly, Wi-Fi also receives all the transmission and then they need to check whether they are being addressed or not. Now, it is not so simple like this. It much more complex things come up, and then different frequencies they will be receiving. So within the Wi-Fi range, there will be different, FDMA is there, frequency division multiplex. Then multiple frequency ranges will be there, and only the devices which are tuned to that particular frequency may receive. So others may not even look at it. Similarly, when they receive and then they want to communicate back, they also need to have some time, okay, in which they are supposed to transmit. Now, let me tell you the issues with the transmission coming from the device, the client device to the router. What this device transmit, it is also the antenna is here. Each of them, normally our laptops have the antenna behind the screen. If you don't know, it is on the part of the screen, and it is not coming out like this. It will be hidden inside. So they will be transmitting it. Now, this transmission that devices do also is received by other devices in the range. So it is open to everyone who is listening to that particular frequency of this wireless communication. So that is why it's called inherently multiple access. Many devices can access the signal which is being transmitted. So it is difficult to direct wireless signals to a particular device. Okay, as I said, the antennas, directional antennas, the construction is difficult. Okay, you cannot hide it inside a laptop screen and expect it to be directional. You have to have a proper design and dimensions to make it directional in a particular way the signal has to be transmitted. So normally even the laptops, when they transmit back, everybody will be listening in the vicinity. Hence, media access control is challenging to avoid eavesdropping. Eavesdropping means somebody who is not addressed and who is not supposed to see the receive the signal, they may also be receiving the signal, and they will also be processing it. So we need to make sure that our Wi-Fi signals are protected by encrypting it. You might have seen that AES2 or AES, some protocols will be there, encryption protocols, which are used as a part of the wireless signal, so that nobody else will be able to understand it unless they have the key of the transmitting device, the public key or private key communications. Okay. Now, wireless medium is error prone because of external noise and interference. So because this is mostly the Wi-Fi routers are using this frequency which is in ISM band. As I mentioned that we don't need to get a permission to switch on our Wi-Fi router. That means they operate in this ISM band, 2.5 gigahertz, okay, and 5 gigahertz, 2.5 and 5 gigahertz. These are the two frequencies these Wi-Fi routers are using. Now, what happens is, because of even your neighbor's Wi-Fi also will be using the same frequency, there will be interference from multiple signals which are being transmitted in the region. Wireless links are shared among devices in terms of frequency and distance. As I mentioned, this bandwidth, whatever this particular router has, is divided among all the devices which are connected to this particular device. Okay, in your home, if your laptops and the TV as well as mobiles are connected, they all share the same router. Receivers need to take care of multipath reception. So one more thing is, when you have in a building, when you have kept a router in one corner of the house, they send signal in all direction and they get reflected back. And your laptop is here, it is receiving the signal from here, as well as the same signal is getting received after some delay by the laptop. So it is called multipath. There are different paths the same signal is received, and the receiver should be intelligent enough to process it and make sure that they don't get confused. So there is a multiple path reception and signal collision. Signal collision happening because of all the devices are communicating in the same frequency range, so they may collide at the receiving end. So that collision also can happen. Now, one issue which is very obvious in this wireless communication devices, imagine this is the range what is shown. This device B is in the overlapping region of the A and C. Assume that they are all devices which is communicating. Okay, now assume that these are all Wi-Fi routers. They are trying to reply back to the device. Now, when this A is transmitting it, B is also receiving it. Similarly, when C is transmitting it, B is receiving them. Okay, but they may operate in different frequencies that they don't overlap or collide with each other. But the issue here is the A, which is sending it, does not know that there is another transmitter. Maybe suppose you assume that A is transmitting in frequency F1. Similarly, C is also transmitting at the same frequency F1. Now, what happens in a Ethernet world? You might have heard about CSM CD, CSMA CD. If you remember Ethernet communication, carrier sense, multiple access, collision detection. So when this device in Ethernet is a common medium, Ethernet cable is common medium, and then multiple devices are there. When they suppose, imagine situation that there is one device here, this is A, and this is B, and this is C. Imagine A is sending a packet to B, or maybe addressed to B or somebody else. C is also sending the same time. You know that in Ethernet, the same device cannot communicate on the same cable simultaneously because they will collide. Now what happens is, if A is communicating, it is sending the signal as well as sensing it. Again, it is trying to see whether there is a collision of the signal happening or not. Now, if another device C is also transmitting at the same time, then what happens is it takes some microseconds for this signal to come here and then get received by A. Similarly, A is also transmitting it. So during that time, if this device is also communicating, then A will come to know, because this signal which is sent by C is also received by A. Similarly, what A is sending is received by C. So they will know, A and C will know that that signal, that packet I sent got collided. Even if they have not addressed to B, it may be for some other device D, because it is all using the same common channel, the common wire, that signal will be corrupted. Now what will happen is both A and C will, they will back off, and then they will wait for a random amount of time before they transmit again. That's a protocol used in Ethernet when they are communicating over the same cable, because they can sense the collision detection. That's a CMCD is they can collision detection they can do, and they can recover from it. That is because they are using the same cable, and the signal can be felt by both of them. Similar technology, similar thing is used here also, that when A is transmitting, it is also sensing whether that transmitted signal is getting collided with some other signal or not. If that problem here is, it is getting collided at B because both of them are sending in F1 frequency, but C does not receive what A is sending because the range is only this much. So it doesn't know that A signal has come. It is also transmitting at the same time in the same frequency. Similarly, A doesn't know that C is transmitting in the same frequency because it doesn't receive what C is transmitting, because it is in the up to this point only the signal is reaching. That is what is called hidden node problem. But B will receive both and they will get collided. Now B gets no signal at all, it gets disturbed, but A and C thinks that they have successfully transmitted the signal because they don't see the collision happening. Okay, but this is what is called hidden node problem in wireless. This is exposed node problem. Okay, let me explain this. You have multiple devices. Okay, all of them are able to transmit, but the ranges are different. Okay, you can see the circle shown. Now what if A is, so B to A, suppose you assume that B is communicating with A. Okay, assume B is communicating with A, similar to what I said F1, the same frequency it is communicating. Now this signal, whatever B is transmitting, is up to reaching only up to this point. D is not receiving it, but C is receiving it. But C can send it to D in the same frequency F1 reliably, because D is not getting collided with the F1 at that time. Correct? Because D is out of the range of B. But C does not know that D is not in the range of B. So it thinks that if I am getting collided with the signal, even the other device also may be there or may not be there. It doesn't know, but it knows that it is in its range, but it will not communicate with the D, wasting that particular channel time, because it thinks that it may be colliding with the signal, because it is seeing that it is busy because B is transmitting in that signal. It doesn't know whether D is in the range or not. This is called exposed node problem. So though D is not exposed, C thinks that this node may be exposed to B and it doesn't send it. So it's a wastage of the bandwidth. But successfully it would have sent it. You may wonder how can it successfully send it in F1. So let me explain. C is addressing to D using F1. Assume that. It is only these two should be receiving it properly. Okay. D will be receiving it properly, no problem. Similarly, B is communicating with A and A should receive it properly, it will happen. Whatever C is transmitting, it will not reach A because the range is only this much. So A and D will not get collided. At the receiving end, it should not get collided because the transmission is happening from the node B and C. So on the receiving side, if they are received properly, no problem. Even if the transmitter is seeing the collision, the receivers are not seeing the collision because what D is transmitting is not reaching A, what is B is transmitting is not reaching D. So I hope, sorry, not D is transmitting, C is transmitting. Means what I hope, let me explain again in case you have not understood. Let me tell you, B is transmitting to A in frequency F1, it is received properly, no issues. Similarly, what C is transmitting in F1 is addressed to D, it is received properly because this transmission of B is not reaching D. Similarly, this transmission of C is not reached A, doesn't reach A. So both on the receiving end, they are not collided. Okay, I hope this is clear. It's these two things may be useful. I thought I will let you know. Okay, now let us go into 8.2.11. This is all IEEE standard. All of you may be aware that this is the Electrical and Electronics Engineers International Organization, wherein even I am also a senior member of this organization. This actually standardizes anything which is across the world needs to be done. Even the USB or all the protocols, everything is standardized by this, and they give some number also. They do a RFC, request for comments. So the standards committee will be there. They will be asking for comments from different participants and companies which are involved in standardizing it, and then they come up with a standard for each of the protocols to be used across the world. So this is the number given for to them by them for the wireless communication, Wi-Fi communication. Now, how does Wi-Fi work? Just a very high level overview. This is the access point. You know that access point is the one which is radiating the signal and receiving it from other devices. Now, when these devices are transmitting, they send it back to the access point, and then when multiple access points are there and then they are all in the same network, it is like multiple switches are there connected to the same network. They go through the distribution system, which is nothing but a level 2 switch, L2 switch, and these packets get routed through them and then switched through them. Okay, I cannot use routing for L2. So the packets go around this area. Okay, so in case if I will tell you that what is happening. So an access point connects the wired router. Okay, normally what happens is if you are having in our home, Wi-Fi is transmitting it locally and then it is connecting to the service provider, internet service provider through a optical cable or whatever, so that it connects to internet, okay, through them. So one side is Wi-Fi, all the devices talk to this Wi-Fi and then they go through the ISP. So similarly, even if you have multiple in a railway station or an airport, we have multiple access points, or a college or a in a closed environment where a huge campus, they all connect to the backend network and then they connect to the internet in the back. So APs are connected to each other. Now what happens when they need to communicate? Okay, only through this network, okay, this distribution system. Now suppose A wants to send it to F. A wants to send a packet to F. Now they cannot go through directly. Of course, they are not in the same range. Even A and C will not communicate directly. Some protocols allows it. Otherwise, there will be some peer-to-peer communication is there. I'm not saying that this is standard, but in Wi-Fi, what happens is it goes to a access point and then goes to C. Okay, and now what if A needs to communicate with F? It goes through distribution system, A to AP1, AP1 to AP3. Okay, or through the distribution system, maybe multiple stages may be there. That's why I'm showing it here, and then AP3 may be there, which is it finds out from the, you know, that there are so many protocols which are learning the different devices in the network, and then they know that F is there in this port, and they go to AP3 and then finally land into F. So this is how the communication happens. That's why if you see a packet of wireless Wi-Fi packet, it is also similar to Ethernet packet, okay, ETH packet, but in ETH, what you see is destination MAC address and source MAC address only will be there. Only two addresses will be there in a normal Ethernet communication. Whereas we have wireless, there are, sorry, this is not the one. There are three of them and then one more. Four addresses are there. Okay, they are all MAC addresses. You can see 48-bit shown here. MAC addresses are 48 bits. So this is address 1, address 2, address 3, and address 4. Okay. Now, if you can remember that network byte order we discussed earlier, and then we said that it is a big endian, it follows. That's why address 1 is first given, and then address 2, then 3 and 4. Because when A is communicating to F, who is receiving that? AP1 is receiving the packet first, and it needs to know to which address it is supposed to send, which is the data, this distribution system. So it is processed in the order in which the packet, not a packet, I should say that it is a datagram, gets routed, okay, switched. So it receives in this order, so it processes in this order. So that's why always the value which needs to be processed first is put in the beginning, and that is how it is also transmitted in the network byte order. Okay, then payload comes and CRC, which CRC I mentioned it in the last class. So each AP operates on some channel. Okay, it's not that only one frequency they operate. They have multiple channels so that all of your laptops can communicate in parallel with your Wi-Fi router. So no collision among APs in the overlapping region, because they are using different channels. There may not be any collisions. So this is what I mentioned: a router, a Wi-Fi router, access point, AP. This is a router which is connecting to the internet, and Wi-Fi network. It is having a Wi-Fi network. You may have a router connected to other wired network also. You may see that in your router you will see some Ethernet cables are there. You can directly connect to them and then communicate with the net. So if you are not on Wi-Fi, okay. I hope this is clear. So wireless router connects a group of wireless stations to a wired network. Okay, this is just how different devices are connected to the internet. I hope this is clear. Now, before I go into Wi-Fi 6, the latest technology on Wi-Fi 6. Okay, nothing, no questions. So we will go. How many of you are there now? Only 13 are there. I don't know what is happening. Anyway, if you think it is not useful, I don't know. Okay, Wi-Fi 6. Now, what is the latest and greatest Wi-Fi technology which is there, which is meant for IoT now? Okay, this is basically this has come up. This standard has come up, taking care of the IoT requirements. Now, let me explain why it is and how is it helping. Now, AX is the standard 802.11. Now, it enables next generation Wi-Fi connectivity having higher capacity, okay, in terms of data rate, coverage, number of devices covered, as well as range is not huge, but the amount of devices, number of device density is more. Performance, the latency is very low. As I mentioned, hyper dense environment where you have many devices. That's why I'm saying this is meant for IoT, because in normal Wi-Fi, we don't expect to have more devices around it. Whereas in Wi-Fi 6, which is meant for IoT, we have many number of devices connected to the network. So hyper dense environment, the Wi-Fi 6 works. These networks enable lower battery. Okay. Now, when I say it is meant for IoT, it has to take care of battery operation. So power consumption is less and perfectly suited for IoT and smart home and smart city applications. It uses, I mentioned about this multiple input, multiple output and multi-user. That means it uses multiple antennas. The router or the access point, what I showed earlier was single antenna, but here it will use multiple antenna. I will tell you the reason for that. And it also operates on two frequencies, 2.4 GHz and 5 GHz. Okay. Both are ISM bands. Now I will tell you why we need multiple antennas and what is the advantage. When you have multiple antenna, what happens is when both of them transmit the same frequency, on the receiving side, they can make sure that they overlap in such a way that they add to the signal, they add the signal to each other so that it is directional to the particular device. That means when 2 or 3 antennas are transmitting in the same frequency, it will add up in phase and they transmit it with some delay based on the distance between the device and the antenna. They change the phase means the phase of the signal is like when a signal is there, if you have 90-degree phase shifted means it is shifted like this 90-degree. This is the phase phi. So they change the phase of the signal what they are transmitting based on the distance of the device and the way they are positioned, so that the transmitted signal they add up on receiving. So what happens is they get more energy. Even if you're transmitting less signal, they get added up and the receiver sees more energy on receiving it. So noise immunity is there. Apart from that, other directions, the signals will be cancelling out. So the other devices in the vicinity, they may not see this transmission at all. That means you are having a directional transmission by having multiple antennas. That's the thing I am trying to say. Single antenna is omnidirectional, whereas if you have multiple antennas, they can be directional, and by that you can enhance the signal as well as remove the interference, so that other devices also can communicate with some other transmitter in the same frequency because they are not overlapping. So that is the advantage of MIMO technology, which is multiple input, multiple output, having multiple antennas. So this kind of beam forming, as I mentioned, beam forming is a technique which focuses on wireless signal towards a specific receiving device. Okay, this is very important. You need to understand this because it is going to be useful in Bluetooth also to understand how the latest Bluetooth version finds out the distance of IoT devices from the transmitter. Okay, I will talk about that. So it can sense the direction, okay, as well as that how much distance it is also there. So they can pinpoint a particular device in the array environment so that they can do a localization, or they can locate the particular device in a region. Okay, so that is very important feature of Bluetooth, as well as it is enabled in Wi-Fi also, in Wi-Fi 6 in specific. Okay, so they are used in both 5G also and Wi-Fi 6 also, that you can have beam forming is there. Because of that, higher data rate is possible and power efficiency is possible. When I say power efficiency, the transmission need not have to be more powerful because they are getting added up in the receiving end. So they can send half of the power and they will still get a better response or receiving on the receiving side. So okay, little bit understanding of wireless will help you a lot to when you read up some material, you will have a better understanding. Okay, even though if you don't have studied this in a subject. Another important thing which is specific to IoT is target wake up time. See, what happens is, I will tell you, you have a transmitter. Let me assume that it is a Wi-Fi router and there is an IoT device. Now they normally send beacon, okay, that I am there, okay, and this is the distance and this is the frequency I'm transmitting, so that the IoT device can communicate back. Okay, sometimes the devices may say that this is the time you are supposed to transmit, so that the IoT device can send it back in during that particular time. Now what happens is, even when Wi-Fi router is transmitting it, Wi-Fi routers do not have a power consumption problem because they are connected to power normally. But IoT devices are operating on batteries, so they cannot transmit as powerful as Wi-Fi router or as frequent as a Wi-Fi router or AP, okay, or access point. Now what happens is, when the IoT devices need to look for the communication from the Wi-Fi, they have to wake up every few seconds or millisecond. They have to wake up to know what is the communication coming from the AP. Suppose some data has come for the IoT device, it will communicate to the device saying that data is available. So IoT devices go into sleep and then wake up and then they communicate with the Wi-Fi or access point. Now what happens is, this target wake up time feature of this Wi-Fi 6 enables the IoT devices to know, the AP has to, it will tell in advance that you can sleep for some time. Okay, I will not disturb you. I won't expect you to be awake till this time. Okay, so that IoT devices can sleep for that much time and then only wake up during the scheduled time for it to receive some data from there or to transmit some data from here. So frequently they can keep sleeping and then waking up, and then they can update the AP and then cloud so that the data from IoT devices get updated. Suppose temperature sensor or pressure sensor, they can sleep for more time when they are connected to Wi-Fi 6 compared to any other devices or a technology. So this target wake up time is one of the features which helps in saving power for the IoT devices. So this is a feature you should understand how it helps for the IoT devices to sleep and then wake up and transmit whatever data it wants, if it knows that it can sleep for some sufficient time, which is possible with Wi-Fi 6, so that Wi-Fi 6 send it to all devices different sleep time so that they all can sleep and then they wake up at that particular time and then communicate back to the AP. Okay, I hope this is clear to you. And one more advantage, one more enhancement is done. Now they have added a new frequency also. 6 gigahertz is also added to Wi-Fi 6 now. They can be operational from 2022. So now we have additional bandwidth, additional frequency band, which is ISM band, freely available for the IoT devices to communicate. Okay, if the IoT devices are having sensors which can make use of the 6 gigahertz band, as well as the routers are compatible. Okay, they also can transmit in 6 gigahertz band. So the data rate is gigabits per second. So you can even stream live HD audio or HD video using the Wi-Fi 6. Multiple devices can stream simultaneously. That is the beauty of Wi-Fi 6 and what it helps, how it helps in terms of IoT. Okay, so I am not going to talk more about Wi-Fi. Any time is what? Let me see. Okay, already 36. In case of router with multiple APs, multiple antennas or APs, okay. The DHCP server and routing table are in router only or shared to each and every APs, and also MAC binding info is in router or APs. See, okay, let me talk about it. Do I have, oh, one note I have not taken it up. Let me address it. Okay, see what happens when you say multiple APs are there. See, there is no central point of routing or something. Okay, multiple APs are there. The information about each of them. Okay, suppose this is the, some devices are there, and then there is a distribution system. Now, what happens is the information is shared across. You must have heard about source routing. Not a source routing. It's called a source routing is one term or one protocol, wherein initially what happens is, suppose a device A is there and F is there here. Its MAC address is something MAC A. This is MAC address is MAC F. Now, source routing is some technique which is used for identifying which device is in which AP. Okay. Now, they maintain the addresses of MAC addresses of AP1, AP2 may be pre-configured, or they will learn from the they learn source port learning, self-learning or whatever. I forget the name of the learning. The L2 level, they do the learning of different devices and its MAC addresses which are connected to the AP. So different APs. Now what happens is when this guy is trying to communicate with F, it doesn't know that that particular device is in this AP or not. Then flooding happens. Okay, they do a flooding. This packet is sent to all the ports in the network. All of them receive. The beauty of data link layer is if they are not addressed to, if they are not addressed, then they will drop the packet. So they do the flooding initially, and the learning happens due to the when they reply back, when F replies back to the A, then F's position will be known. So they do the learning, each of the devices do the learning based on the initial flooding happens, and then the learning happens. So I forget the name of this protocol. If anybody remembers, my memory is very weak. That is source protocol. I forgot. Okay. So they learn the path or the position where they are available. So they are maintained at each of those devices. Most likely, okay, they will be because these things will be removed also because they are time bound. You don't need to have like a IP router in a core network. They don't have to maintain the routing table entries for all the devices, because once a laptop comes up here and then it moves to the another AP, this entry will be lost based on the time. If the packets don't come from there, there will be a timeout for the entries to be removed from the routing table. So the MAC address, MAC routing table is normally what happens is gets added and then removed dynamically. So, and too many devices won't be there. So it can be maintaining the thing on individual APs, or it depends on the configuration. If there is actually it is mostly, if my understanding is correct, AP1 will be maintaining it. Okay, I hope my answer is okay. One more thing, IoT devices are built to have a long life and are installed in places which are not easily accessible. Okay, how they do, then do they keep up with the different advancements in technologies which keep coming up in software update enough? Okay, it's a good question. I wanted to bring up in one of the protocols which are coming up. Okay, which is I mentioned about LTE. LTE is on the on the base station side. They can update the software and then they can make it enable for different technologies. But it is not true. Suppose if you have built an IoT device with Wi-Fi 5, okay, 5 standard, okay, and then you don't expect this IoT to work with Wi-Fi 6. Now, how they manage is normally these Wi-Fi routers are backward compatible. Okay, they have to be backward compatible. Even it is true with the USB, Bluetooth. All of them new technologies are backward compatible. You can see that when you have a USB 3 on your laptop, suppose you have a USB 3 on your laptop, and then you have a USB pen drive which is USB 2. When they communicate, when they are connected, they exchange information first. Okay, what are you? Are you supporting USB 2 or USB 3? They do a service discovery protocol and then understand what version of the device is on the other end. So when the USB 3 knows that the other end is a USB 2, then what happens is they start communicating in that speed, because normally what happens is USB 3 is much higher rate. They can transmit signal in a much higher rate if the receiving end also is capable of receiving it. If it is also USB 3, they can communicate and they can talk to each other in USB 3. But if the other end is USB 2, still it works. USB 3 works with USB 2. Similarly, Wi-Fi 6 router, if you bring a new router in your home, but you have a mobile which is old enough and it is only 5, then they can still communicate. Your mobile can communicate using Wi-Fi because the frequencies are same, 5 gigahertz and 2.5 gigahertz, whatever, and dual band Wi-Fi. So it can operate in dual band. So they will sense what is the other device protocol and they will communicate. Okay, so IoT devices, yes, I agree that software updates are possible and they are done, but some things which are very hardware specific, protocols are mostly hardware specific, they cannot be upgraded. Okay, but the backward compatibility helps in terms of still extending the lifetime of those devices. They don't go out of life, or they cannot go out of use because of you advancing in the technology. Okay, so I hope this answers your questions. Let me go further. Bluetooth. Okay, I was working on Bluetooth in way back in 2000 when it was introduced when I was in Motorola. Now, what it was 20 years back and now what it is huge difference. Okay, it was 97. It was introduced. Multiple companies were involved in defining the standard. Initially, only 5 companies were there. Okay, it's a short-range wireless communication technology. Uses the ISM band between these two frequencies. Even though it says 2.4 gigahertz, you have to say no that it is between these two. Okay, Bluetooth cannot use everything else. Just 2.4 gigahertz doesn't give you full information. But I don't want you to mug up these numbers. But keep in mind that this ISM band is not only reserved for Bluetooth. Okay, it is used for oven, microwave oven, and mobile. Cordless mobile, and then different medical equipments, and then even some defense radars use them. So there are so many devices using the ISM band. It's not only even Wi-Fi router. I mentioned that Wi-Fi also uses this 2.4 gigahertz. So, but they use different frequencies so that they don't overlap with each other. Okay, when you are putting them together in the same place, your oven is also on, your Wi-Fi router is also on, you are also connected on Bluetooth with your mobile, with a TV. All of them work because they are all protected because of the frequencies as well as different modulation techniques they use. They understand each other. They still live with each other, and even your neighbor's Wi-Fi is also overlapping with your own Wi-Fi. No problem. Now, how is it defined? It is defined by a special interest group. It's called SIG group. We call it a SIG. It is in the US, New York. I think there's a Bluetooth SIG headquarters is in US, which is having around 36,000 member companies. So companies are members, and you and me can become a member to get updates on what are the latest technologies available. I want you to go to the bluetooth.com and then register yourself so that you get a latest update on what is happening on Bluetooth. And then there are actively working groups. Okay, there are 14 working groups. They will be working on different technologies and what is the next version of Bluetooth specification to come up with, and what are the different areas you can make use of the Bluetooth technology, like exchanging of majority. I am going to come to that. What are the different applications we can use Bluetooth for? So people who are continuously using, are continuously innovating, and then coming up with different things. Okay, one is the hardware, Bluetooth hardware. Okay, and then what communication and OFDM and other frequency modulation, those things needs to be decided. What frequencies to use needs to be decided. Okay, and then what is the data rate is available that you can use in that particular hardware. All that needs to be done. And then there is a Bluetooth stack that needs to be developed. And then this is Bluetooth stack, the software protocol stack. And then we also have a profile, Bluetooth profiles. That means it can be used for audio streaming or data exchange, or it could be for file transfer, that is the same as data transfer, or it can be for other applications, I forget, mesh networking. So there are different things you can use it for. So there are different profiles defined, how to interface your application with the profile. So there are standard code available and a stack available, and the complete implementation is available, and the devices are there. It's a open source. Okay, so this design is available. So you can, different IC companies, OS companies, and then protocol stack companies, they are part of this 36,000 members. So they all do different things at the same time to introduce a Bluetooth technology to the world. So it's a combination of work happening in the background for years together to come up with Bluetooth, a new Bluetooth standard. So then once it comes up, then all the mobiles and other devices, audio equipments, everything, they embed those Bluetooth chips, and then they start using it. So that's why you can see that a Samsung TV with a LG mobile, they communicate with each other because of this standard. Okay, there is nothing like who is building it, which software is running, doesn't matter. So Bluetooth has been growing exponentially for 2 decades, and they also have a location services. This is what I was mentioning it. Bluetooth has a location services. That is a one major important application profile which is used. Now in IoT, what happens is we want to have a Bluetooth enabled key, car key, suppose car key. That means when you are holding the key and then coming closer to the car door opens because they communicate with each other because of the Bluetooth enability. And then suppose in your home you have kept your key and then you don't know where it is, you can have an app in your mobile and it will exactly direct you to the place where your Bluetooth enabled key is on a table, or even it has fallen below the table, you will be directed towards that. So the Bluetooth 5.2 version, which is the latest version, has the location service. It can identify a device, a Bluetooth enabled device, IoT device in particular, where exactly it is from your another device. Okay, it is like a peer communication. So it is nothing like a AP. Master is there, but it is every device can communicate with any other device, peer communication. So they can communicate with each other, pair it, their pairing happens, and then they can exactly sense the direction as well as the distance between them, so that it can direct you to the place where the key is. So you can imagine using the Bluetooth 5.2, you can evolve new applications, IoT applications, and your imagination is only the limit. Okay, you can use this technology for any other application wherein you want to know exactly where the device is and what is the range and what is the location, angle also you can see. So these kind of different profiles they come up with a new technology to enable such a capabilities, location services. Okay, and this Bluetooth 6 standard to market, it is manufacturer must meet the standard. Okay, what happens is when the Bluetooth is introduced on a devices, they need to cater to the 6 standard. That means they will come up with some test cases and test profiles. This SIG gives you, and then you need to pass all of them, and they need to certify you before you can put your software and hardware into your device to be able to communicate with any other Bluetooth device, because they are controlling the standard of Bluetooth. Okay, I hope this is clear to you, the beauty of Bluetooth. So I will stop with Bluetooth today. I don't think I can go further. So master slaves are there. It's a piconet. Okay, it's called piconet. Maximum 8 devices including the master can be there. 7 slaves and 1 master. And master initiates the communication. Okay, and then what happens is it provides the time when the slaves can communicate. Okay, they decide the time at which each slave device in the Pico net can communicate. So it is like this. Okay, when you have a classroom, you have a lecturer, and our students are there. Suppose students want to talk to each other. What happens is the master can say that, okay, during this particular time, you two communicate, and then during this time, maybe you two can communicate. So they give you different time. So because already decided, they talk only during that time. So any other device in the piconet, they don't get disturbed and they can still communicate. So that's the beauty of this master slave. Master slaves doesn't mean that everything needs to go to the master to come back to slave, similar to Wi-Fi. But here they can peer-to-peer communication happens, but master decides when each of them can talk. Okay, so that synchronization has to happen. So what is the important thing? Because it has to exactly time it when it is they are supposed to communicate. That means all the clock in these devices need to be synchronized. That's why synchronization happens using some other protocol, so that there is a drift in the clock which needs to be adjusted so that all of them can have a same clock, so that they understand the time gap and they communicate during that time. Okay, that is what is called synchronized. So clocks of the slave devices are synchronized with the master. Okay, now and then the slaves can communicate over the slotted time. Okay, by the master, so they communicate with each other. Now another beauty is they need not have to be in one network only, like a piconet. You can sign up with different piconet, and they can be a slave on one network, and then they can be a master on another network. and they can communicate. So scatternet is called scatternet. So devices can be on multiple piconets. So these are the something which you should know about Bluetooth. Now don't worry about this layer, very simple. It's like a OSI layer, radio layer, baseband layer is similar to MAC layer, and then L2 cap is something like a TCP IP combined together. Okay, but it is in L2, so it's not even L3. It's a MAC layer only. I can say it's a MAC layer. So radio layer is a physical layer wherein all AR interfaces, what frequency hopping, they use multiple frequencies on the same. Okay, 79 frequencies are used, so don't worry. So it's called MAC sublayer. They use TDMA. I have already explained to you. Half duplex I have already explained. And L2 cap is L2 is nothing but L square. Okay, L square cap. That is logical and link. That is why two L are there. So L square. Logical link, control and adaptation protocol. They combine different. No, this is the protocol which is running on both on the master and then slave, and they communicate. Okay, so simultaneously a slave or a master can communicate with multiple devices. So that kind of a communication is possible. That's why this adaptation layer mixes the data between multiple communication happening. Okay, so you can pair with multiple devices also in your mobile, right? You might have seen that. So frequency hopping spread spectrum is used just for your knowledge. Version 5.2, as I mentioned, is the latest version on the Bluetooth, which is very popular for audio. Okay, low energy audio, for audio streaming. Okay, audio streaming happens during this time. That's why you can use your Bluetooth enabled headset to communicate with your speaker. Okay, that's a very popular usage, and they can control the power transmitted by the devices. Okay, that's why you can reduce the interference among the devices. So this much is enough on Bluetooth. Let me see whether there are any questions, and time is already up more or less. So okay, no questions. Should I stop here, or I will complete the Bluetooth, or at least I will be, yeah, I have done it. One market update, I will send it to you. You can see them. It's not a very thing, no, just for knowledge sake. I have given a link also, I think. You can read it. It's very interesting to know about different Bluetooth technologies. One thing I will tell you, what are the use cases? Audio streaming is one use case, wherein the headset can be connected to the speaker. Lots of audio speakers are now Bluetooth enabled. 97% of devices which are coming in the audio world or cars, they are all Bluetooth enabled. They can exchange data, file transfer or whatever, and location services I already explained to you. It is useful for different IoT purposes. And mesh network is one major advantage of Bluetooth. It supports mesh network. That means multiple devices can be there and they can communicate with each other. Okay, I will talk about mesh network when I go to the Zigbee in the next class.